So next we want to talk about inverse functions. So what is an inverse function? We want to think of an inverse function as a function that undoes another function. So what do I mean by that? Let's think about it in terms of our potato diagrams. If I have a function, f, and let's say it sends 1 to A, 2 to B, and 3 to C, so it's nice and easy, then my inverse function should send A back to 1, B back to 2, and C back to 3. So it's going to basically reverse the arrows. Of that function f. So that if we do f and then we do the inverse, we should get back to where we started. So if I start with some x, I do f to it, and then I do f inverse, I should get back to where I started. And as we said before, composition is not commutative, so it turns out we actually have to be able to do it in the other order as well. And that one should also give us x. So before we get sort of too deeply into talking about inverse functions, we want to use this idea of reversing the arrows to help us think about what kind of functions can have inverses. Okay, so I've got two functions drawn here, f and g. And I want to think about what happens if I start trying to reverse my arrows and think about whether I could get an inverse function. So for f, if I just redraw my two sets, so let's actually label these guys. I'm going to redraw my two sets exactly the same way as they are right now. And I want to think about reversing the arrows. So I'm just going to change the direction of those arrows. And what I should see here is that I end up getting something that's not a function, right? So this 1, when I reverse the arrows, it would have to get sent back to two different things, and that makes it not the function. So why did that happen? Well, over here, right, this was okay for being a function, right? This was just not injective. It was not one-to-one. But when it's not one-to-one, then when I reverse the arrows, then it becomes not a function, right? It's not well defined because that single element got sent to two separate elements. So therefore, right, a function must be one-to-one to be invertible. That's the first thing we can notice. So let's look at the second example. This one is one-to-one. So again, let's label these guys. I'm going to switch it around. So I'll put them in the same spots as they are right now, but I'll reverse the order of my arrows. And I'm going to think of this as my domain because that's the starting point, and this is my codomain. And again, I run into a problem here because I have this element in the domain that doesn't get mapped to anywhere. So again, this is not a function. And then it's still not well defined, right? Well defined means both of these properties. Everywhere must get mapped to somewhere. So it's just not defined at all. Where this one wasn't defined well because it got sent to two different places. We'll kind of break it down like that. So here, we notice that the problem that we run into is that it wasn't onto, so there was something that didn't get mapped to. So a function must also be onto to be invertible. And it turns out that's all we need. So as long as a function is one-to-one and onto, so as long as it's injective and surjective, so as long as it's a bijective function, then it'll be invertible, because when you switch the order of those arrows, you'll still get a function going back the other way. Okay, so now that we have these ideas down, let's go ahead and look at some formal definitions. So remember that we defined functions in terms of relations. So we're actually going to define an inverse relation first, and then we'll talk about when a function has its inverse relation, which is also a function, which is kind of different language about the thing we've already talked about. So let's see what that looks like. So if I have a relation from A to B, so remember that's just a subset of the power set, the inverse relation is going to be a relation from B to A, and you're just going to switch the order of each of the elements in your ordered pairs. So if xy was in the regular relation, yx is going to be in the inverse relation. Now, if you have a function, f, then it's bijective if and only if its inverse relation is a function from A to B. So that's what we showed, right? So when we were switching the arrows on those potato diagrams, what we were really doing was we were changing the order of our function. So we were changing the order of that ordered pair in our relation. And we saw that if they had that the inverse was a function, so that inverse relation is a function when the function was one-to-one and onto, and then as long as it's one-to-one and onto, then we're going to get that that inverse is a relation. So that's exactly what we saw previously in that last example, just all tied up into our theorem now. And now we want to kind of be able to talk about these inverse functions in terms of compositions, right? So if you do the function and then the inverse, you get back to where you started. So the way we'll sort of talk about this idea of back to where you started is this identity function. So an identity function is just a function from a set to itself, defined by if you take in x, you get back x for every x in A. So the function f of x equals x, right, that function, you take in x, you just give back the same x, that's my identity function. We usually think of that as the identity function on R, because here I'm thinking about this function f going from R to R. But from any set, you can basically define that same function, and that's going to be your identity function. So what does that have to do with an inverse? So if you have a bijective function, it has to be bijective in order to actually have an inverse, then the inverse is just the function that goes the other way from B to A. And it obeys that if you do first f and then its inverse, you get the identity on A. So you start with something in A, you do f to it, you do f inverse, you get back to A. And if you start with something on B, you do f inverse first and then f, you get back to where you started. So that's sort of our other way that we can think about these identities, or the functions that you can compose with the original function to give you that identity. So we'll see some examples of that in the next slide. Okay, so what we have here is a function, and we'll hold that it's bijective, right? So I have this basic function, f of x equals x cubed plus 1. So let's draw that in here. There's my nice axis. X cubed plus 1 is going to look something like this. So we can see that it is going to be one-to-one because it passes that horizontal line test, and it's onto. It's going all the way up to infinity, all the way down to negative infinity. So it is bijective, and now we want to find its inverse function. So we can really find inverses the same way we're used to doing it in algebra. I'm going to do something a little weird, and it's not what the book does. And what I'm going to do is I'm just going to take my function, and I'm going to solve for x. Traditionally, what we do is we swap x and y and solve for y, but there's no real reason to do that. I could just solve for x and then get the inverse function where y is my variable. So I'm going to get that y minus 1 is equal to x cubed. So x is equal to the cube root of y minus 1. So that's my f inverse of y. It's equal to the cube root of y minus 1. If instead I wanted to ask you what f inverse of x was, then I just change the variable from y to x, so I could say it's the cube root of x minus 1. So either way of doing it is fine. So now we could check if this really works, just to kind of check our algebra. So I want to check, is f inverse compose f of x equal to x? And let's check both orders, f compose f inverse of x equal to x. Well, let's try. That's f inverse of f of x. F of x is equal to x cubed plus 1. So I'm going to plug x cubed plus 1 in for my y. So I get the cube root of x cubed plus 1 minus 1. So that's just the cube root of x cubed, which is just x. Over here, I get f of f inverse, which is the cube root of, here I said f inverse of x, so I should actually plug in x minus 1. I could have also said f inverse of y equals y. Maybe that would make more sense, because usually when I'm thinking about my function, the inputs are the x's and the outputs are the y's. So the inverse may want to do the opposite way. So I get that. Let's put in that y there. And then I'm going to add 1. What am I doing? Sorry. F inverse f of that. And then f of that is you take that thing, you cube it, and then you add 1. So we get y minus 1 plus 1, which is just equal to y. So when I do f first and then f inverse, I get back to x. When I do f inverse and then f, I get back to y, because I started with y. So that is what we wanted to show. Great. Okay, for discussion question here, I want you to see if you can find the inverse of f of x equals x squared. And if you can't find that inverse, can you restrict the domain and the codomain so that you can? And then once you restrict the domain and the codomain, what is the inverse of that function? So see if you can kind of figure out how that all works together.